Hello, in this lesson we will study multiple angle formulas, power reducing formulas, half angle formulas, and product to sum and sum to product identities. These formulas allow us to rewrite trigonometric expressions into forms that are easier to evaluate, simplify, and solve. We will also see how they can be used to solve trigonometric equations and transform one expression into an equivalent form. Let's get started. In this lesson, we will learn several important trigonometric tools. First, we will use multiple angle formulas such as the double angle and triple angle identities. Next, we will use power reducing formulas to rewrite powers of sine and cosine. We will then examine half angle formulas and use them to solve equations. Finally, we will learn product to sum and sum to product formulas, which allow us to rewrite products as sums and sums as products. These identities become especially useful in higher mathematics courses, including calculus. Let's begin with the multiple angle formulas. The double angle formulas express trigonometric functions of twice an angle in terms of the original angle. Notice that the cosine double angle formula has three equivalent forms. Depending on the problem, one form may be more convenient than the other. The tangent double angle formula is obtained from the tangent sum formula by setting the two angles equal. I encourage you to become familiar with these identities because they appear frequently throughout trigonometry and calculus. In this example, we solve the equation 2 cosine x plus sine 2x equals 0. The key observation is that the equation contains a double angle. Whenever you see sine of 2x or cosine of 2x, consider replacing it with a double angle identity. After substituting the identity for sine 2x, we can factor out a common factor of cosine x. Once the expression is factored, we use the zero product property and solve each factor separately. Notice that one solution appears in both sets. We list only that solution once in the final answer. This is a common technique when solving trigonometric equations involving multiple angles. Now let's divide the triple angle identity for sine. Instead of memorizing the formula, now let's derive the triple angle identity for sine. Instead of memorizing the formula, it is useful to understand where it comes from. We rewrite 3x as 2x plus x and then apply the sine sum formula. Next, we substitute the double angle identities and simplify. The Pythagorean identity allows us to replace cosine squared x with 1 minus sine squared x. After distributing and combining like terms, we arrive at the important identity. Sine 3x equals 3 sine x minus 4 sine cubed x. This formula frequently appears in advanced trigonometry problems. Power reducing formulas allow us to rewrite squared trigonometric functions using first powers of cosine. These formulas are derived directly from the double angle identities. Their primary purpose is to eliminate squares and make expressions easier to simplify, integrate, or compare. You will often use these formulas when working with higher powers of sine or cosine. This example demonstrates why power reducing formulas are useful. Our goal is to rewrite sine to the fourth power using only first powers of cosine. We begin by writing sine to the fourth as the square of sine squared. Then we substitute the power reducing identity for sine squared, x. After expanding the square, we encounter cosine squared 2x. Since that term is still squared, we apply a power reducing formula to a second time. After simplifying and combining fractions, we obtain an equivalent expression involving only cosine 2x and cosine 4x. The graphs shown on the right confirm that both expressions produce exactly the same function. Half angle formulas allow us to find trigonometric functions of half an angle. Notice the plus or minus sign in the formula for sine and cosine. The correct sign depends on the quadrant in which the half angle lies. Again, this is one of the most common mistakes students make when using half angle identities. Always determine the quadrant before choosing the sign. The tangent half angle formula can be written in several equivalent forms, all of which are useful depending on the problem. In this example, we solve a trigonometric equation involving a half angle. We begin by replacing cosine squared of x over 2 using the half angle identity. Notice that the square eliminates the plus or minus sign, which simplifies the work. After substitution, the equation becomes a polynomial expression involving cosine x. Factoring produces two possibilities. Either cosine x equals 0 or cosine x equals 1. Solving each case gives the solutions shown on the slide. The graph provides a visual confirmation that these values are indeed the zeros of the equation. Next, we introduce the product to sum formulas. These identities convert products of sine and cosine functions into sums or differences. Although they may seem unusual at first, they are extremely important in calculus, physics, and engineering. Whenever a problem contains products of trigonometric functions with different angles, these formulas often simplify the work considerably. Let's use a product to sum formula to rewrite a product. We identify the expression as cosine of 5x multiplied by sine of 4x. The appropriate identity converts a cosine sine product into a difference of sines. After substituting the angles and simplifying, we obtain an equivalent expression involving sine 9x and sine x. The graph shown on the slide illustrates that the original product of the resulting sum produce exactly the same function. These formulas perform the opposite transformation. Instead of rewriting products of sums, they rewrite sums or differences as products. This can be useful when solving equations because factored expressions are often easier to analyze. Notice the symmetry between the product to sum formulas and the sum to product formulas. Learning when to move in either direction is an important skill in trigonometry. In our final example, we solve the equation sine 5x plus sine 3x equals 0. The expression is a sum, so the natural strategy is to apply a sum to product identity. After rewriting the expression, we obtain two factors, sine 4x and cosine x. Using the zero product property, we set each factor equal to 0. Be careful with the equation sine 4x equals 0. This means 4x equals n pi. So the solutions occur at multiples of pi over 4. Combining these solutions with the solutions from cosine x equals 0 gives the complete solution set shown on the slide. The graphs on the right confirm that the original expression and the transformed expressions are equivalent and share the same zeros. This example illustrates the power of sum to product identities when solving trigonometric equations. This concludes this lesson, and I'll see you in the next one.